Hey guys, so today we're starting the next chapter with our Introduction to Solutions lesson. A lot of this stuff about solutions will be stuff that you're already familiar with, but we'll just review it, and there's probably going to be a couple new things as well. So this is our Introduction to Solutions. We're going to be going over the difference between a pure substance, a homogeneous mixture, and a heterogeneous mixture. You need to know some definitions, including solution, solute, and solvent. We're going to briefly talk about how solutions can be made of matter that are in different states, so like solids, liquids, and gases. We're going to talk about why dissolving as a process is important. You have to know the difference between endothermic and exothermic reactions, particularly in terms of forming and breaking bonds. We're going to talk about how much energy it takes to dissolve ionic and molecular substances. And we're going to differentiate between electrolytes and non-electrolytes. So a lot of different things. First of all, are different types of substances. So a pure substance is a substance that is made up of only one type of molecule that cannot be separated by physical processes. So it could be separated chemically, just not physically. Pure substances include elements, so anything on the periodic table, but it also includes compounds. So H2O, if it's by itself, if it's pure water, would be a compound. Obviously, tap water would not be because it includes H2O as well as like dissolved minerals and stuff. Same with like CO2, carbon dioxide is a compound, it's a pure substance. If it's in the air, then the air as a whole would not be a pure substance because there's also nitrogen gas and oxygen gas, but each one of those individual gases, those individual compounds are a pure substance. A mixture then contains more than one type of molecule, and there's two different categories of mixture that we're going to be looking at, the heterogeneous mixture and the homogeneous mixture. The heterogeneous mixture is a mixture where the ratio of molecules is not constant throughout the substance. And the way that you can tell that is if you're looking at a liquid or gas, and it's a mixture, it will appear cloudy or opaque. So it'll be hard to see through if it's a heterogeneous mixture. On the other hand, with a homogeneous mixture, that's where the ratio of molecules is uniform throughout. Those mixtures, if they're a liquid or a gas, will look transparent. You'll be able to see through it easily. So yeah, that's how we can tell. If you know that something is a mixture and it's a liquid or a gas, you can tell whether it is homogeneous or heterogeneous based on how easy it is to see through. Yeah, so this is just talking about pure substances, can be either elements or compounds. So again, pure substance, elements, or compounds, and then mixtures are anything that's not a pure substance because there's more than one type of compound, and they can be homogeneous or heterogeneous. Next on to some of our solution definitions. So solution is a type of homogeneous mixture that is made of at least one solute and one solvent. If we're dealing with liquid and gas solutions, they will be clear, again, because it is a homogeneous mixture. A solute is the substance that's being dissolved. So for example, in the ocean, you have a lot of salt dissolved in the water. Or if you just like open up your tap, you would have like chlorine or calcium or sulfur dissolved in your water. We also have oxygen dissolved in our water, so it doesn't have to be a solid, it could also be a gas like oxygen. That's what allows fish to breathe in the water, the fact that there's oxygen dissolved in the lake or whatever. And then the solvent is the thing that the solute is dissolved in. So for example, the water itself. So if we take the solute, the stuff that's being dissolved, plus the solvent, which is the stuff doing the dissolving, and mix it all together, we end up with our solution. Again, solutions can be solid, liquid, or gas. So gases can dissolve in other gases. That's like the air around us. Both gases, liquids, and solids can be dissolved in liquids, just like oxygen in water, alcohol in water, salt in water. And gases and solids can also be dissolved in solids to make solid solution, just like oxygen can be dissolved in solid ice, tin can be dissolved in copper to make like an alloy solution, stuff like that. Alloys are just a special type of solid solution that is made up of two solid metals. When you're dissolving substances in water, usually you're doing that in order to initiate a chemical change. In order for a lot of different chemical changes to happen, you have to dissolve the substances first. A lot of different ionic compounds, those are ones where you have a metal bonded to a non-metal, they can react in a double or single displacement reaction in order to make a precipitate when you have them in solution. However, if they're not in solution, a lot of ionic substances won't react with each other at all, or will react with each other really slowly. There are definitely some exceptions to that. Yeah, a lot of the time, in order to get those ions to react with each other, you have to split them apart from the ion that they're currently bonded with, which you do by dissolving them in water, and then they'll be able to react with some of the other ions that are in solution. In polar solvents, like water, ionic compounds will dissolve really easily since the dipoles of the polar substance, that's the slightly positive end and the slightly negative end, will attract the positive and negative ions and pull that ionic compound apart. Once the ions are pulled apart, again, they're free to react with the other ions that are in solution. Usually we see evidence that that chemical change has taken place in the form of a precipitate. So a precipitate is an insoluble substance, so it's a substance that won't dissolve in the water or whatever your solution is. So it will precipitate out, or it will form a solid that usually sinks to the bottom of your solution. Endothermic reactions and exothermic reactions are definitely things you've heard of before. Endothermic reactions are reactions that absorb energy. They require energy for the reaction to take place, and they feel really cool to the touch because they're literally like sucking the heat out of your hand. Exothermic reactions, on the other hand, release energy to their surroundings, and because they're releasing energy, we feel that as heat coming off of like the beaker or whatever. Anytime you break bonds, that is always an endothermic reaction because it takes energy to break that bond. And then anytime you form a bond, it releases energy. So that's an exothermic reaction. When we dissolve an ionic substance in water, those ionic bonds, the bonds that are holding that ionic compound together, have to be broken. Those are intramolecular bonds, bonds within a molecule. So we have to break those ionic bonds apart in order to dissolve the ionic substance. This is called the dissociation reaction, the breaking apart of an ionic compound like sodium chloride into the individual ions is dissociation, and that is always an endothermic process. Then we're going to form new bonds between those ions and our water molecules. That's why this ion has broken apart in the first place, is because the sodium, or the positive ion, is forming a bond with the slightly negative end of the water, while the chlorine ion, or our negative ion, is forming a bond with the slightly positive end of the water molecule. Anytime you have those new bonds formed, that's an exothermic process. If the energy needed to break apart that ionic substance, to break those bonds, is higher than the amount of energy released when the bonds reform, then the dissolving process is endothermic. However, if I release more energy when I form bonds than when I break them apart, the process of dissolving will be exothermic. So you can never actually tell if the entire process of dissolving is going to be endothermic or exothermic unless you do it in a lab and actually just try it out and see. Different substances will react differently. Some substances will dissolve and it will be an endothermic process. Other substances will dissolve and it will be an exothermic process. So you have to determine it experimentally in order to actually figure out which one it's going to be. There's no way to just calculate it. Non-polar molecular substances don't dissolve in water. They will only dissolve in other non-polar solvents. We usually remember this as like dissolves like. So polar substances can be dissolved in polar solvents. Non-polar substances can be dissolved in non-polar solvents. A polar molecule dissolves in water. Once again, you have to experiment to figure out if it's going to be endothermic or exothermic. However, when molecular substances dissolve, they don't become ions. They actually don't break the intramolecular bonds at all, those covalent bonds. And instead, you just form an intermolecular bond, the dipole-dipole. Those molecules will break. That's going to be endothermic, and then new intermolecular bonds will form, which of course is going to be exothermic. Okay, something that you will have to be able to identify is whether or not a substance is an electrolyte or a non-electrolyte. If it's an electrolyte, then when you dissolve it in water, your solution can conduct electricity. If it's a non-electrolyte, when you dissolve it in water, the solution will not conduct electricity. Electricity needs ions or charge in order to move. So that's why anytime you have ions, that is going to be conductive. Ions are really good at moving electricity since they are charged themselves. So the more ions you have in solution, the more easily the electricity can move through that solution. So ionic substances are always electrolytes. Most molecular substances are not, because they're neutral, they don't form ions, they don't form crystal lattice structures, and therefore the electrons of electricity can't move through them as easily. So for each of these following, I want you to predict if they are going to be water soluble, meaning that they can dissolve in water, and if they are going to be electrolytes. We'll go through the first one together so you can kind of see the process of doing this. Okay, so to figure out if this is going to be an electrolyte or not is pretty easy. When we're trying to figure out if it's an electrolyte, question mark, what we're really looking for is what type of compound are we dealing with? So is it ionic or is it covalent or molecular? If it is ionic, that means it's going to be an electrolyte. If it's molecular or covalent, it is a non-electrolyte. So that part is pretty simple. Methane, which is CH4, is made up of only nonmetals. Therefore, it is molecular or covalent, which means it is a non-electrolyte. Finding out if it's water soluble is a little bit more tricky. So is it soluble in water? The first thing that we're going to look at is, once again, is it ionic or is it covalent? If it's ionic, it's pretty simple. If it's ionic, it is going to be soluble. However, if it's covalent, we then have to figure out if it is polar or non-polar. And to do that, we have to look at its shape. Look at shape. That's how we figure out if they are polar or non-polar. If it's polar, it will be soluble. If it's non-polar, it's not soluble. So with methane, we already know that it is a non-electrolyte. I'm then going to come down here and I'm going to draw methane, CH4, which looks like this. Its shape is a tetrahedral because my central atom, which is the carbon, has 4 things bonded to it. Those 4 things are all the same, and there are no unpaired electrons around my central atom. So because of that, it is going to be non-polar which according to my chart here tells me that it is non-soluble. Okay, so pause here, try the next three, ammonia, beryllium oxide, and hydrogen sulfide, and figure out if they're soluble and electrolytic or not. Okay, next up with ammonia, first thing I see is that both N and H are non-metals, meaning this is a covalent compound, and therefore it's not an electrolyte. Then I'm going to draw out my ammonia. So nitrogen has 5 bonding sites. 3 of those are going to be taken up with a hydrogen, like so. And feel free to do like your full sausaging method if that's easier. I just happen to know what shapes these are all going to make. So this is a trigonal pyramidal, which you might just know that that shape is always polar, or you can see that our central atom has unbonded electrons. And anytime a central atom has unbonded electrons, it is going to be polar. And in this case, polar means that it will be soluble in water. Next up, we have beryllium oxide. Beryllium is Be, oxygen is O. This is an ionic compound because we have a metal and a non-metal, which also means I should be crossing my charges when I write the formula. But these both have charges of 2, so they cancel out. So that is what beryllium oxide actually looks like. And because it's ionic, I know that it is an electrolyte. Okay, and then I don't even have to draw this one out. If I go back to my lovely charts here, I only have to look at the shape if I'm looking at a covalent molecule. If I'm looking at an ionic molecule, I know right away that it's soluble. So ionic also tells me that it's soluble. Okay, and the last one here is actually a bit of a trick question. Hydrogen sulfide, H2S. Now, both of these are, of course, non-metals, so this is covalent. However, some of you might remember from grade 10 or from earlier that anytime we have an H at the beginning of a compound like this, other than water, that means that this is an acid. And acids and bases don't behave like normal compounds. So this is not going to behave like a normal covalent or molecular compound. Acids are going to act differently. And what you need to know about acids is that even though they are covalent, if they are an acid, they will also turn into an electrolyte. I know, that's tricky. But acids do a process similar to dissociation, like ionic compounds do when the ions split apart. Acids go through a similar process called ionization, which we'll talk about later on in this unit. But because of that, they also become electrolytes. So this is an acid, therefore it is an electrolyte. And when it comes to solubility, acids are always soluble. So acid means it's soluble. The one little trick that you need to remember when it comes to acids is even though an acid is often a covalent compound, acids act like ionic compounds, even though they aren't. Okay, so just keep that in mind. The same is also true for bases. Bases will act like ionic compounds, even though they're not. So whatever you would normally do for an ionic compound, the same will always be true for an acid as well. Okay, so again, if you're checking whether it's an electrolyte or not, if it's ionic or an acid or base, it'll be an electrolyte. All other molecular compounds are non-electrolytes. If you're looking to see if it's soluble in water, if it's ionic or an acid or base, it will be soluble in water. For all other molecular or covalent compounds, you have to look at the shape in order to determine if it's polar or non-polar. If it's polar, it will be soluble in water. If it's non-polar, it's not soluble in water. Okay, if you have any other questions about that, please let me know.